Good afternoon, ladies and gentlemen. Welcome to the second part of the PhD defense of Erik Tengs. My name is Bernhard Müller. I've been appointed to chair the PhD defense. I'm a professor at NTNU. The Faculty of Engineering has appointed an evaluation committee consisting of the first opponent, Professor Thomas Staudi from Lucerne University of Applied Sciences and Arts in Switzerland. And the second opponent, Professor Sanda Georgescu, University Polytechnica of Bucharest, Romania, and myself. For those of you who attended the trial lecture in the morning, it will not come as a surprise that it was approved by the evaluation committee. So we can continue the procedure, and that will be now the PhD defense. So Erik, as I mentioned in the morning, holds a Master's of Science degree from NTNU of 2016. You were supervised by my colleague, Associate Professor Paul Turostoli from the Department of Energy and Process Engineering of NTNU. And the co-supervisors were Professor Ole Gunnar Dahlhaug and researcher Dr. Chirag Trivedi, who unfortunately cannot be here. They are also from our department and also from the Hydropower lab. In addition, the third co-supervisor has been technical consultant Martin Oswald Holst from EDRMedeso in Sandvika, Norway, who is here. So now it is your turn. But before I would like to announce, after the presentation by Erik, we'll have a 5-minute break before the discussion starts by the first and the second opponents. But now the floor is yours, Erik, with the title of your PhD thesis, Numerical Simulation of Fluid Structure Interaction in High-Head Francis Turbines. Please.
Thank you. Again, welcome everyone on our committee, professors, family and friends, to my PhD defense, titled, as said, Numerical Simulation of Fluid Structure Interaction in High-Head Francis Turbines. It's quite a mouthful, and hopefully it will make a little bit more sense in about 45 minutes. The setup will be similar as earlier today. We'll go through a little bit on the background. We will look at the mechanical phenomena of resonance. The main part of the presentation will be a numerical workflow for simulating these phenomena, before we will end with a little bit on modal order reduction. To start, I'm just going to show a picture of a Francis turbine. Not everyone here is familiar with what that is. The main focus of my research has been the heart, the rotating runner of the turbine. You should also be aware of all the stationary components surrounding it. And we will see later that these components actually affect the rotating runner in the center. What started all this, the whole project that my thesis is a part of, is headlines like this. This was late 2011 or early 2012. It's in Norwegian, but it says runner crack at Svartisen. Svartisen is one of the more prestigious plants in Norway. It is, I think it's the largest turbine in terms of power that we have. It's a high-head Francis turbine. It is located in the north of Norway, and it had a catastrophic failure only 200 hours after installation. And of course, in 2011, you shouldn't have such a complete design fail in a brand new turbine. So this is what kickstarted everything, and after this, things started moving, and after a while, this project, High Francis project, started to actually look into why this is happening, and is there something we can do to avoid this. And one of the first things you do is to look at the history. Is this an isolated incident, or is this something that has happened before? These are data from one of the large turbine manufacturers. I think it's about 300 or 400 turbines. These are turbines, Francis turbines, that has experienced cracks during the first 2 years of operation. And these are binned after decades, and it's in percentage of installed turbines. And a couple of things, there is no real trend here. It's hard to say if this is decreasing or increasing, but we could see that this has been a problem for as long as we have recorded data. So Francis turbines have always had some chance of failing during the first few years of operation. Even more interesting is if we take the same data, but we bin the turbines according to available water head. And we see that virtually all the failures are in the range of 400 meters and above. This is something we call high-head Francis turbine or very high-head Francis turbines. And in this group, there's close to a 20% failure rate, which is ridiculous, to be honest. So 1 in 5 of these turbines break within the first 2 years, historically. So we have a type of turbines, the high-head Francis turbines, and they seem to break, and it's always been like this. At the same time, in 2012, Seidel and friends in Voigt published the following figure. Many of you have seen this before. It's a paper where they classify what type of dynamic phenomena affects what type of Francis turbines. What you see here is on the left side of the x-axis is the high-head Francis turbines, marked here. And according to this, these high-head Francis turbines have a large impact from something called RSI. And what is RSI? Well, RSI is rotor-stator interaction. This is what I mentioned earlier. Because you have something that is rotating inside some stationary components, you have some interaction between the two. So every time a rotational blade passes a stationary blade, something happens. And it's easy to imagine that there has to be some acceleration of the fluid, there has to be some deacceleration of the fluid, pressure pulses that are created and propagated through the system. The thing is, we now have turbines that fail. We know that RSI is the reason or the main dynamic source of load, and we even know the frequency of this phenomena. But still the turbine fails. So somehow we are unable to calculate the actual load of this phenomena. And now we have narrowed the problem into what I'm going to talk about today, calculating the load inside these high-head Francis turbines. Next up is resonance. I guess most of you have heard of resonance. If you want to explain this in one sentence, we could say if a small load is applied at the right place and at the right time, then the amplitude of vibration can be magnified outside of control. You could have catastrophic failures. In most textbooks, this is visualized using a swing, because this is, everyone intuitively understands the swing example. Also as illustrated here. And everyone can see why this isn't working. The guy here, his father, I guess, is pushing at a frequency that is way too high. If he was a little bit more patient, the swing would gather momentum and the kid would have a better time. Resonance you'll find in all systems. Researchers in California have recently discovered that if you don't adjust your step, you'll spill your coffee within the first 10 steps. That's good to know. And in more serious cases, we have, for example, the Tacoma Bridge collapse back in the 40s. This is a concrete bridge, and this is excited by the wind. So you can imagine this magnification that we're talking about here. This is also a nice example of a glider plane in unfavorable conditions. This resonance phenomena is what we believe is the reason for many of these failures in the turbines. So now to the main part, the numerical workflow. First, I'm just going to mention the geometry we've been working on. First of all, we've been working on the Francis 99 model runner. It is located here at the university. It's open source. You'll find geometry, experimental data, everything online. What I have focused on primarily is the onboard pressure taps. So we have alongside one channel, we have several pressure taps that can measure the pressure inside the runner, and that's the load, that's the pressure field we are interested in. That's what makes the blades fail. Additionally, we have been looking at a simplified model of a blade named the Francis hydrofoil. It's a linear hydrofoil, and it is also open source, geometry online, experimental data online. And in this experimental rig, we have looked in more detail at the physical phenomena of damping. The workflow I'm going to present looks like this. We will go through all the different modules here, starting with CFD analysis. And what is CFD? CFD is basically a numerical simulation of fluid flow. You could have a semester of teaching CFD. I'm not even going to try to tackle this. If you're going to break it down to a series of simple steps that you have to go through, you have to discretize your domain. In all numerical simulations, you have to take a part of the real life and you have to discretize it. You have to apply some sort of boundary conditions, if that's mass flow, if it's pressure, rotation for that matter. And finally, you solve the Navier-Stokes equations, which are the governing equations for fluid flow. When doing CFD, you can get everything you like in the flow field. You can get streamlines, you can follow particles, you can look at pressures, you can look at turbulence phenomena, and so on and so forth. So it's a wonderful tool if used correctly, and it is becoming one of the most important research tools in fluid mechanics and hydraulic research in general. You can find all this, but my main focus, as I mentioned, have been on the pressure inside the runner, and specifically the pressure in the 4 points that the experimentalists have gathered data. Here you have an animation of the pressure field. A couple of interesting things. You can see, first of all, there seems to be sort of a up and down motion and oscillating motion through the channels. which means that if we were to plot this in one point, we will see some variations. You can also see that there is some sort of rotational motion here. There seems to be some global pressure field. The channels are not experiencing the exact same pressure at the exact same time, which means that there are some variations in the circumferential direction as well. We'll get back to what this means a little bit later on. If we pick one of these pressure taps in the runner and we plot the CFD data with the experimental data, we get a very good correspondence. There is a slight offset that's due to boundary pressure condition, which is basically just a numerical artifact. If we plot this instead in the frequency domain, we see that the amplitudes and frequency correspond very, very well. Except, as some of you might have seen, what I would refer to as the missing pressure. This is the third pressure probe in the channel. The first harmonic of the pressure field is almost dead on. And what we see here is the 360 is the full runner is simulated. The frozen gust one is when you only simulate a couple of channels and you use some tricks to get the full pressure field. Both of the methods match the experiments very, very well. But what's going on here? For some reason, we are under-predicting the experimental pressure by 75% or more. So what is this pressure? What's the phenomena that we are unable to simulate? This is my first paper, and of course back then I had no clue what was going on. Hopefully we'll see in a while what that pressure is. If you see in all the pressure probes, these are the pressure probes sequentially along the channel. You'll see that every single pressure probe, this is the amplitude of the second pressure harmonic. You see that all the pressure probes are consistently under-predicting the experimental pressure. And not only under-predicting the pressure, but also missing this trend. The trends aren't even the same. So it's not a factor of error. In experiments, we see an increase in some of the probes in the channel. In the CFD, we do not. So this is basically the background for the project. Because if you remember resonance, if a small load is applied at the right place and at the right time, then you can have a catastrophic failure. So if this is the right time, and we underpredict the load by 75%, then our lifetime estimators will be useless. And that was the basis for the further work here. And we did have some questions. What is this? Are the simulations wrong? What is the missing pressure? And we will get back to some of this. Moving on, we have the modal analysis. Modal analysis is a study of vibrational characteristics. And what does this mean? First of all, I can go through a series of similar steps as in the CFD. You need to discretize your domain. We are now on the structural side of things. You need to discretize your domain, here illustrated by a turbine runner. You need to apply some boundary conditions. And what you solve here is something called an eigenvalue problem. And in an eigenvalue problem, you get two things. You get an eigenvector and an eigenvalue. Physically, this corresponds to a natural frequency and a mode shape. And a mode shape is the vibrational shape of a structure. This is illustrated here by just a fixed beam. The three first mode shapes of this beam And each of these mode shapes have a corresponding natural frequency. In a turbine, you have something called nodal diameters. So these mode shapes can be generalized into something that we have borrowed from disk dynamics, that a turbine mimics the motion of a disk. A nodal diameter is a line of no deformation, which means that in this figure you have one line, meaning ND1. In this figure you have two lines of no deformation, which is an ND2, and can look something like this. Of course, massively exaggerated, but this is the global shape of the vibration in the runner. Now we can finally move on to an assessment stage, where we ask, is there a risk of resonance? And that's a quite hard question to answer. But as I said in resonance, if a load is applied at the right time and at the right place, then something bad can happen. So obviously we need to compare the load from the CFD with the vibrational characteristics from a modal analysis. So if we start with the spatial distribution of the load, this should match then the mode shape. This is the pressure field, and this is a mode shape, and it doesn't seem like these correspond at all, so it shouldn't be a problem. We have to consider, though, that in terms of vibrations, we're not looking at the absolute pressure field, we're looking at the pressure fluctuations. So if we decompose this pressure field into a mean component and its fluctuating components, it can look something like this. And some of you will probably see that these correspond, which means that there is a potential risk of having resonance here if the frequency matches the natural frequency of the runner. And comparing frequencies should be fairly straightforward. And it will rarely match perfectly. But how far away can it be to be safe operation? Is 5% enough? Is 10% enough? Is 20% enough? I know several companies use 20% as this safety factor in terms of how far away you should be from a natural frequency. I'm just going to illustrate here how dangerous that can be. This is a dynamic amplification factor. I have created this by applying a load in an harmonic manner, an oscillating load, and I have extracted the vibrational amplitude. I have divided this number by the amplitude if the same load was applied statically, which means then this is actually just a visualization of a resonance issue. What we see here, for example, is that at the eigenfrequency, the amplitude is about 75 times higher than if you just apply the load statically. So it shows the danger of resonance. And let's say you are 20% off. You have then a magnification factor of about 2.5 maybe. And that's okay, you can add some safety factors elsewhere. But let's say your calculations of the eigenfrequency miss by 10% or something like this. Suddenly you're here, and your magnification factor is 10. And all your fatigue calculations will then be useless. So suddenly you have a load that is a lot higher than you thought initially. So the safe thing, of course, is not to use this rule of thumb to assess, okay, we are in a safe region. The safe thing is to continue along this workflow and actually getting a number quantifying this issue. This is done in a harmonic analysis, but before we go there, we need one critical input, which is the damping factor. The damping, well, first of all, damping is a mechanism that extracts energy from a system. If there were no damping, you would have infinite vibrational amplitudes, or you will have vibration that lasts forever, none of which are physical, of course. In terms of a structural analysis, this is one of the key inputs. The fluid that surrounds the structure, the vibrating runner in this case, of course, exerts some sort of pressure field on the runner and also damping. This is called hydrodynamic damping, and one of the main research focuses for me have been to calculate this damping numerically. How we do this is start off with a modal analysis, and from modal analysis we get something like this. Now I'm talking about the hydrofoil geometry, as you can see. We then scale this vibration to realistic amplitude. This is of course completely unrealistic. We scale this to a realistic amplitude and we load it into a CFD analysis. We then let the water flow across this hydrofoil, which is now oscillating, and we extract the work on the blade or the work on the water from the blade. In a real-life situation, this work from the blade onto the water would be energy that is taken from the blade and damping the oscillations. We take this work and we normalize it by some factors, and we use this as an estimate of this damping, the hydrodynamic damping. Carl, who's in the audience, have done experiments, and I've done this numerically, and we compared the damping, and we get a very good correspondence between the numerics and the experiments. When you have an estimate for the damping, you're finally ready to do an harmonic analysis. And what is an harmonic analysis? Well, we are in the structural domain, first of all. And opposed to modal analysis, you're now looking for the actual amplitude of vibration. A modal analysis is undamped, it's unloaded. This simulation is damped and loaded. So you get the actual deformation due to an actual load. Similarly, you need to discretize your domain. You need to apply boundary conditions, and in this case you solve the harmonic equations, which is the second order oscillating system expressed as a harmonic set of equations. In step 2 here, when you apply boundary conditions, that applies also to the CFD load. So the pressure field from the CFD analysis, which was the first step in this workflow, is then applied onto the structure as a boundary condition. The damping that we obtained in the previous step is also implemented, and you solve this, and this as well is exaggerated motion, but you get some deformation shape that can look something like this. And this is now, not in the animation, but the result is now the actual deformation due to this CFD load. Two words about something called acoustic elements. This structure is submerged, and because of this, there are two phenomena we have to consider. When a structure is submerged in water and it wants to vibrate, it has to displace the water around it. This water has a density, a weight, and it will exert a force, an opposing force to this vibrating structure. This phenomena can be modeled as if the structure itself is heavier. It's then called the added mass effect. I haven't mentioned it explicitly, but the natural frequency of a structure is inversely proportional to its mass, which means that if the structure is heavier, the natural frequency will be lower. And again, because of resonance, because you have to compare loads and vibrational characteristics, it's highly important to calculate the correct natural frequency. So having this added mass effect is of absolute importance. And I think not doing this correctly is probably one of the reasons that many turbines have failed in the past. Another factor that you have in these acoustic elements is something called the acoustic pressure. The acoustic pressure is actually best known as sound pressure. When you hear the speaker, it is because the speaker is creating a pressure pulse, and this pulse is traveling through the air, and your eardrums is interpreting this somehow. The air in front of the speaker is not moving towards you, it's only the energy that propagates through the medium. This kind of motion is governed by the wave equation, and in these acoustic elements there is only one degree of freedom, which is a pressure governed by this wave equation. The easiest analogy I found was this. Everyone have done this, two people holding a rope, and you can send a wave across this rope. So the rope isn't going anywhere, in the same way that acoustic elements in the structural analysis are stationary. There's no bulk motion, but it acts as a medium that can transmit energy. So this is one pressure component. The pressure from the CFD is another pressure component. And now we are going to add them together. This you've seen before. This is the second pressure harmony, the amplitude of the second pressure harmonic in all the pressure probes in the experiments, and with CFD only. If we were to add the acoustic element, the acoustic pressure from the harmonic analysis, it looks like this. So suddenly the whole issue of the missing pressure, as I called it, is gone. There is some discrepancies at the outlet. That is due to some details in the bolting of the Francis 99 model rudder. The experimentalists have actually somehow been able to split the pressure signal from the experiments. Don't ask me how. So this way we can actually compare the convective or viscous or CFD pressure experiments versus numerics, and it's almost spot on. And this was exactly what we saw in the first harmonic as well. We are able to simulate this phenomena. And then we have the acoustic component here, and again we have some discrepancies at the outlet. And I think this is the first time this is shown, because the experimental data was only released a month ago in another PhD thesis, and it's very good. It shows us that the CFD was not wrong, and it shows that this workflow of separating the pressure into two components is working. Well, so to sum up this, of course the missing pressure, the phenomena we were unable to simulate in the CFD analysis, is then the acoustic pressure. I should also say by now that the acoustic pressure will only appear, or will only have a substantial impact on the pressure when you are close to resonance conditions. As you saw earlier, this graph that showed the amplification factor, if you are way off the natural frequency, the contribution will be close to 0. That's why on the first harmony you only see the CFD pressure, while on the second harmony, which is close to resonance in the model runner, you have a contribution from both the CFD, the incompressible CFD, and from this acoustic pressure. To summarize the workflow, if you have a CFD analysis and you load this pressure onto a structure in a harmonic analysis with a reasonable damping estimate, you will get the same pressures as you do in the experiments. And that's a tick off. However, there is one more issue we need to talk about in numerics, and that is time consumption. Some of you are familiar with these procedures, some of you are not. A simulation like this, let's say you simulate just one rotation of the runner. It takes, in real life, a fraction of a second. On a supercomputer, hundreds of computational cores, it can take weeks. Just one runner revolution. Let's say you have this pressure field, you load it onto your structure, you want to look at sensitivity with respect to damping, maybe you want to test the sensitivity with respect to where you are in terms of the natural frequency, maybe you want to create one of these plots like this. We're talking additional days of simulation. That's why the final point on the agenda is going to be some model order reduction procedures. A model order reduction, what is it? It's a mathematical field of its own. It can be described as a way of reducing the complexity in a system. I'm not able to give you this 3-point checklist as I have for the other modules, because there is no one-size-fits-all method for this, unfortunately. The principle is, as in the figure here, you're going from something that is complex to something that is a lot easier, but you retain the most important information in the system. This is, by the way, not at all what we've done, but it illustrates the goal very well. As I said, something like this is not possible. You can't just drop a model order reduction on top of this whole procedure. I'm going to just briefly mention what you can do in some of the modules. On the CFD side, there is one dominating procedure, and that is using frequency-based methods. One of the most time-consuming things in a CFD analysis is the time-stepping procedure. You need a time resolution that is very good. You need to resolve all transients, so on and so forth, which can be fixed by using frequency-based methods. Another thing you can do with frequency-based methods is actually to reduce the domain in space as well. So this method actually works in space and in time. What you do is actually you use the fact that this runner is rotationally symmetric. The pressure field have certain global shape, certain circumferential variation. You can actually use this as a boundary condition, periodic boundary conditions on just a section of the runner. You can specify that whatever goes in on one side is not what goes out on the other side right now, but it was what went out on the other side maybe a fraction of a second earlier or later. So it's a so-called phase-shifted periodic boundary condition. We implemented this and we got a speed up of about 5, which is very good. That's the difference between a day and a week. You can also take it one step further and actually rewriting the Navier-Stokes equations into this harmonic form. You're basically going from a time discretization to a frequency representation. You have to decide in advance what kind of frequencies you're looking for, so you need to have some knowledge about your system. In this case, you could specify that we want to look at the RSI frequency, and then we can solve for the amplitude of the pressure. Instead of stepping in time, we're using a steady state solver. This could, in theory, give, well, here I'm actually showing it. You express your full pressure as a mean pressure and higher harmonics, and you do this in advance, and then you solve in this frequency domain. This could, in theory, give spectacular speedups, but this has been, in my experience, a bit unstable as of now. But in the future, I believe this is going to be the go-to method. Next up, harmonic analysis. This is in the structural domain. What we are looking at here, this is starting to be a little bit technical, but you have an original system. You want to use some sort of vectors to get a reduced system. It is in one way what you saw in the figure earlier, where you go from a complex, very detailed system to a simpler one. What you need to do, of course, is to find the set of vectors that makes the reduced system resemble the original one to the best degree possible. Krylov vectors is a vector space that does exactly that. It is fairly advanced mathematically. What we do in essence is that we take the transfer function, which is basically the dynamic response of a system, and we express this by a series expansion, which means that the more vectors you add to this series expansion, the closer you get to the actual dynamic response. We then implemented this into ANSYS, the numerical software, and we ran a series of cases where we compared the full solution from ANSYS to this model order reduction procedure. And the results were close to numerically perfect. This is on the hydrofoil, and we see in the line is the reduced model, and the crosses is the full ANSYS solution. Another example here, the same, the reduced order model in the line. And here in this case, with low damping, we actually see that the reduced order model is better at finding the exact point of resonance. And most importantly, the speed up is very, very good. It is always in 1 order of magnitude faster, in some cases close to 40, 50 times faster. Of course, dependent on how many frequencies you are to investigate. The very last method I'm going to talk about is related to something I haven't covered at all yet. It is two-way fluid structure interaction. Two-way fluid structure interaction is in most cases, and definitely in the industry, way too time-consuming. If CFD is time-consuming, then you can probably add a factor of 5 on this to get the two-way coupling. But in some cases, it is interesting to have a two-way coupling. In some cases, you need a two-way coupling. That is cases where there is a definite interaction both ways, where the fluid acts on the structure, but also the structural deformation has a feedback to the fluid, which is the case where there is large deformation. Or there could be phenomena that you might not understand fully by doing a one-way simulation, and you want to do a two-way simulation to get additional information, like what is going on with the damping down here? why is there different slopes in this graph? What I did is something that is based on mode decomposition. It is close to what you do in a modal analysis. I expressed the structural deformation as a weighted sum of its eigenmodes. Visually, it looks like this. You have deformation, which is a sum, weighted sum of the different mode shapes. The problem is now how to find these weights. This you can discretize, and you can actually import it into the CFD solver. So that's what I did. I wrote a set of equations. I loaded everything into the CFD solver, and I let the fluid pressure on the hydrofoil calculate the different weights. So how much should mode shape number 1 be weighted, and the second, and so on and so forth. And this way you actually get the actual deformation. So you're not prescribing a frequency in advance, you're not prescribing an amplitude in advance, you let the fluid pressure from the CFD analysis calculate this by the use of the modal decomposition method. And by using this method, we could look at several different phenomena. Maybe one of the more interesting is this one. This is numerical results, where we see that the eigenfrequency, the natural frequency of the hydrofoil, has some sort of shift when you cross the lock-in region. This is impossible to get in a one-way simulation because you would need to specify the frequency of the foil. But in a two-way setting, you can get this. And this is also seen in the experiments, and that's why we try to replicate this. The reason why we have not concluded on, unfortunately. To sum up, I just added a small point here that if you do the CFD, if you do everything, you will get the similar results as experiments, and all of these individual components can be sped up. And by that, I consider myself done. Thank you.